In the high-stakes arena of private space exploration, one name has dominated headlines for years: SpaceX. With their groundbreaking achievements and revolutionary approach to spacecraft design, Elon Musk's company has essentially rewritten the rulebook on what's possible in space travel. But the cosmos is vast, and no single company can claim ownership of the stars. Enter Rocket Lab, the underdog that refuses to be overshadowed. While they've already proven themselves as the premier player in small-scale rocket launches with their Electron vehicle, CEO Peter Beck has set his sights on something far more ambitious. This is Neutron, Rocket Lab's answer to the Falcon 9 and their boldest challenge to SpaceX's market dominance. With its sleek black carbon composite frame and innovative clamshell design, Neutron isn't just another rocket, it's a statement of intent. What makes this spacecraft truly revolutionary is its approach to reusability. Unlike conventional rockets that discard components during flight, Neutron features a captive fairing system that remains attached throughout the entire journey, protecting its second stage like a shield while significantly reducing costs and environmental impact. Powered by 9 cutting-edge Archimedes engines and constructed using the world's largest 3D printer, Neutron promises to deliver payloads to orbit with unprecedented efficiency. But perhaps most impressively, this rocket is designed from the ground up for rapid redeployment, a critical advantage in the increasingly competitive space launch market. With its first flight scheduled for 2025 and contracts already signed with commercial satellite operators, Rocket Lab is positioning Neutron to not just compete with SpaceX, but potentially revolutionize the entire industry and cost its rivals hundreds of millions of dollars. Welcome to Elon Musk 24 Hours, where we bring you the latest developments in space technology and exploration. Let's dive right in. What makes Neutron particularly significant is how it represents a fundamentally different approach to rocket design compared to SpaceX's Starship. While both companies aim to reduce launch costs through reusability, they've taken divergent paths to achieve this goal. SpaceX has opted for stainless steel construction and extreme scale with Starship, while Rocket Lab has chosen carbon composites and a more moderate size with Neutron. This technical divergence creates a fascinating real-world experiment in aerospace engineering philosophies. Industry analysts have noted that competition from companies like Rocket Lab serves as a crucial driver of innovation across the entire space sector. The pressure to outperform rivals forces continuous improvement, ultimately benefiting satellite operators, space agencies, and eventually, everyday consumers who rely on space-based technologies. For Rocket Lab, Neutron represents far more than just a new launch vehicle. It's the linchpin in their strategy to evolve from a small satellite launcher into a comprehensive space services company. With vertical integration across launch, spacecraft manufacturing, and potentially their own constellation, Rocket Lab is positioning itself as a formidable competitor in the new space race. The future of space competition, as Neutron prepares for its debut in 2025, the space industry stands at a pivotal moment. For years, SpaceX has dominated with minimal serious competition. Now, Rocket Lab's methodical approach with Neutron presents the first real challenge to Falcon 9's position. The battle between these aerospace innovators isn't just about corporate success. It represents two competing visions for humanity's space future. Will the carbon composite precision of Neutron prove more sustainable than Starship's stainless steel brute force? The answer will reshape our access to orbit for decades. What's certain is that this competition benefits everyone. As these companies push each other to new heights of innovation, launch costs continue to fall, making space more accessible for scientific missions, commercial applications, and eventually human exploration beyond Earth. Rocket Lab's Neutron isn't just another rocket. It's a bold statement that the space race has truly entered a new phase, one where multiple players drive progress through fierce but productive competition. If you found this breakdown of Rocket Lab's ambitious plans fascinating, help us continue bringing you the latest space industry developments. Hit the like button, share this video with fellow space enthusiasts, and leave a comment with your thoughts on whether Neutron can truly challenge SpaceX's dominance. Don't forget to subscribe to Elon Musk 24 Hours for more in-depth analysis of the companies and technologies shaping our cosmic future. Turn on notifications so you never miss our latest uploads. Thanks for watching, and we'll see you in the next exploration of humanity's greatest space ventures. The engineering marvel behind Neutron. Neutron represents the culmination of years of aerospace innovation and strategic planning by Rocket Lab. The company recently released their Payload User's Guide, the first public step toward entering the competitive heavy lift market currently dominated by SpaceX's Falcon 9. This isn't just a technical manual, it's Rocket Lab's declaration that they're ready to compete at the highest level. Let's break down what makes Neutron truly revolutionary. The first stage booster, with its distinctive, sleek black exterior, is constructed entirely from carbon composite materials, a significant departure from the metal alloys typically used in rocket construction. This isn't merely an aesthetic choice. Carbon composites offer exceptional strength-to-weight ratios, allowing Neutron to achieve greater payload capacity while using less fuel. At the heart of Neutron are 9 sea-level Archimedes engines, Rocket Lab's proprietary propulsion system designed specifically for frequent reuse. Unlike many rocket engines that operate at maximum capacity, the Archimedes engines run at just 90% of their potential output. This seemingly counterintuitive decision actually extends engine life dramatically, reducing wear and tear while maintaining more than enough thrust to deliver payloads to orbit. It's a classic case of working smarter, not harder. The propellant system utilizes liquid methane and liquid oxygen, LOX, stored in common bulkhead tanks, an engineering technique that reduces weight by sharing a wall between the 2 propellant chambers. This efficient design maximizes the rocket's thrust-to-weight ratio, a critical factor in overall performance. But Neutron's most revolutionary feature is undoubtedly its captive fairing system. Traditional rockets jettison their fairings, the protective shell around the payload. Once they reach space, these discarded components typically burn up in the atmosphere or fall into the ocean, representing both wasted materials and environmental concerns. Neutron completely reimagines this approach. Instead of separating from the rocket, Neutron's fairing opens like a clamshell, releasing the second stage while remaining attached to the first stage. This innovative design serves multiple purposes. It protects the second stage during ascent, allowing for a lighter second stage design. It returns with the first stage for reuse, and it eliminates the need to manufacture new fairings for each launch. The cost savings alone are substantial, potentially reducing launch expenses by millions of dollars per mission. The second stage, also crafted from carbon composites, is powered by a single vacuum-optimized Archimedes engine. Unlike the reusable first stage, this component is expendable, either left in orbit or designed to burn up during re-entry. This approach mirrors SpaceX's current strategy with Falcon 9 and Falcon Heavy. What's particularly fascinating is how the second stage is integrated into the rocket. It's suspended by its top flange inside the inner stage at a rigid mounting interface, creating a compact configuration that houses avionics, aerodynamic control mechanisms, and fluid lines. When it's time for stage separation, a pneumatic impulse system ensures quick and efficient deployment, minimizing shock loads and preventing payload contact. Neutron's landing capabilities represent another leap forward in rocket technology. Rocket Lab has developed dual mission profiles for recovery, return to launch site, RTLS, and downrange landing, DRL. In the RTLS profile, after the second stage separates, the first stage executes a complex series of maneuvers to fly back to Launch Complex 3 in Virginia, making a precision landing. This approach eliminates marine recovery operations and allows for rapid inspection and processing. The DRL profile takes a different approach, prioritizing payload capacity over operational simplicity. Instead of returning to the launch site, the booster continues along its flight path and lands on a marine vessel. This requires less fuel for the landing maneuver, allowing more of the rocket's performance to be dedicated to delivering the payload to orbit. Both landing profiles demand sophisticated guidance and control systems. The booster must navigate through varying atmospheric conditions, manage its remaining propellant with precision, and execute burns with perfect timing. To facilitate these landings, Neutron features forward canards and landing legs that extend outward at the base, providing additional stability during descent. The production process for Neutron is equally revolutionary. Rocket Lab utilizes the world's largest 3D printer, a 12-meter-tall, 90-ton, fully automated machine capable of producing carbon fiber composite structures at an astonishing rate of 100 meters per minute. This manufacturing approach not only accelerates production, but ensures consistency and precision impossible with traditional methods. Carbon fiber composites provide substantial advantages over traditional materials like stainless steel, commonly used in rockets such as Starship. While maintaining the necessary strength and durability to withstand space conditions, carbon fiber is significantly lighter. This weight reduction enhances payload capacity, improves engine efficiency, and reduces fuel consumption, creating a virtuous cycle of performance improvements. To protect the first stage during the intense heat of re-entry, the thrust structure is coated with a highly efficient reusable thermal protection system, TPS. This advanced heat shield technology, initially developed and tested on Rocket Lab's Electron rocket, makes it possible to recover composite boosters from near-orbital velocities repeatedly without degradation. Neutron's market strategy reveals just as much engineering insight as its technical design. Rather than rushing to secure contracts at discounted rates, CEO Peter Beck has emphasized the importance of establishing Neutron as a reliable, high-performance vehicle commanding premium prices. This patient approach seems to be paying off. On November 12th, Rocket Lab announced a contract with an undisclosed commercial satellite operator for 2 Neutron launches, one scheduled for mid-2026 and another in 2027, with potential for additional launches. During the third quarter earnings call, Beck emphasized that they've been cautious about marketing Neutron until the vehicle is proven. "Any launch contract you sign is meaningless," Beck stated frankly. "I'd rather enter the market with a reliable, high-performance vehicle that gets a premium price than rush to secure low-value contracts." This strategy aligns with Rocket Lab's target launch price of $55 million for Neutron, positioned competitively against SpaceX's Falcon 9, which costs approximately $67 million per launch. CFO Adam Spice reinforced this position, stating, "We are not going to offer heavily discounted Neutron launches just because it's a new vehicle." The company's launch cadence plan follows a measured growth trajectory. After an initial test flight expected in 2025, Rocket Lab aims to conduct 3 launches in 2026, 5 in 2027, and eventually scale up to 7 or more launches annually. As Beck explained, this gradual scaling follows a similar growth trajectory to what we achieved with Electron. Qualification testing of Neutron's flight hardware is well underway, including vehicle structure testing and Archimedes engine development. The first hot fire test of the Archimedes engine was conducted in August at the Stennis Space Center in Mississippi. Over the past quarter, we've doubled our engine test cadence in Mississippi, and now we have multiple engines on the test stand, Beck reported. Neutron plays a crucial role in Rocket Lab's broader ambitions, which include deploying their own satellite constellation. Beck has described this initiative as the company's third pillar, alongside launch services and spacecraft production. While details about the constellation remain undisclosed, Beck emphasized the importance of having a reusable, high-cadence launch vehicle. Without a reliable, frequently reusable launch system, everything else becomes irrelevant. Drawing a parallel to SpaceX's use of Falcon 9 for deploying Starlink, Beck positioned Neutron as the key to unlocking that potential. Despite Neutron's promising design and advanced technology, significant challenges remain. The lightweight carbon composite structure, while offering performance advantages, raises questions about long-term durability. Unlike stainless steel, which has demonstrated exceptional resilience through multiple launches and re-entries, the ability of carbon composites to withstand the stresses of frequent reuse remains unproven in rocket applications of this scale. Another concern involves the theoretical nature of Neutron's performance. Until the first test flight, key components like the Archimedes engines and clamshell fairing need to prove their functionality in real-world conditions. Any delays, malfunctions, or subpar performance during initial testing could impact Rocket Lab's competitive position against established players like SpaceX. The space industry has witnessed numerous ambitious rocket programs face unexpected challenges during development and early operations. Rocket Lab's ability to navigate these potential hurdles will ultimately determine Neutron's success in the market. However, the company's track record with Electron, which has achieved 59 successful launches to date, suggests they have the engineering expertise and operational experience to overcome obstacles.